Now we find the displacements. So the displacements are in Cartesian polar coordinate system. The displacements are going to be u r and u theta, and we now see a problem where we will find out u r and u theta for using the Mitchell table. So let's say there's a problem where phi is given to be of this form. Now, when we do it in cylindrical polar coordinate systems, we have to remember that all displacements that we determined are undefined up to a rigid body translation in x, a rigid body translation in y, and a rigid body rotation about the z-axis, x3 axis, which will mean that u are of this form where a and b are constants, u theta of this form where again a and b and c are constants, uh, a can always be superposed on any displacement that you find without changing the strains in any way. So the strains will not be affected by these rigid body translations and rotations. So any strain that you find, you can always superimpose this on the displacement and you would keep getting the same strain. It will not be affected. Now, keeping this in mind, we have a Mitchell table for displacements where again, these are the possible terms that you can have in the expansion of phi. And 2 mu r, where mu is the shear modulus, 2 mu theta are given for each of these terms. There is another quantity called kappa, which arises based on whether you consider plane stress or plane strain. Remember that the constitutive equations are different slightly for plane stress and plane strain, and therefore the strains that you get from the stresses are different for plane stress and plane strain, and those differences are carried over to the displacements as well. Kappa embodies that difference, and the value of kappa is equal to 3 minus 4 nu for plane strain and 3 minus nu by 1 plus nu for plane stress. So this is all that we have to remember, and then we have to take these terms one by one and see where they appear in the Mitchell table. For example, let's take the first one, r square sine 2 theta. And r square sine 2 theta, we take this term, rn sine n theta with n equal to 2, which appears somewhere here, rn sine n theta, this one, with n equal to 2, which gives r to the power 2 minus 1, that is r to the power 1 in the two displacements, which means that in the displacements you are going to have r sine 2 theta terms, and then don't forget to divide by this 2 mu because these displacements are given as 2 mu times the displacement. Okay, and the first term in ur will be this. Similarly, you can find the first term in u theta as well, because u theta is also of the same form but contains cos n theta. So for this term, the u theta contains cos n theta. You can work this out yourself. So I am only working out the ur as an example, which contains sine 2 theta. Okay. Similarly, look at, okay, I do one more step. I use this relation where I express the shear modulus in terms of the Young's modulus and the Poisson's ratio, and this is the final term that I get. Let's take the next term, which is sine 2 theta, and this is what we are going to take with n equal to 2. So if you go back to the table, this is the term that I can take with n equal to 2. So there's minus 2 plus 2 r to the power 0 sine 2 theta, and it will lead to this term in ur. Again, I'm not doing u theta. If you did, it would just have the cos n theta. So if you do this and put the correct value of kappa, we are doing plane stress here. If you do the correct value of kappa for plane stress, then this is what you are going to get. Again, I have replaced mu with e and nu to get this expression. This is the second term in the displacement that appears because of the sine 2 theta term in the phi. Okay, and then we are left with the last term in phi, which was this, and then uh, this can be had from r to the power minus n sine n theta with n equal to 2, and that is here, r to the power minus n sine n theta with n equal to 2, and that gives rise to this strain, this displacement, sorry, and that is the last term. And then if you put them all together, ur is, this is what we have got from the table. This is what we have got from the table. 3 terms in phi leads to 3 terms in ur. And then this is the arbitrary rigid body translation that has been imposed. And that is arbitrary. That has always to be imposed, and this does not affect the strains at all. So this is how you have to determine, you have to use the Mitchell table to determine displacements in cylindrical polar, in a problem given in the cylindrical polar coordinate system.